So let's continue with our minimum cost flow problem. I'll quickly revise the whole thing. So we said that we will have a starting solution as a structure TLU, where T is the spanning tree, yes, spanning tree consisting of basic arcs, right. Now these arcs, the flow may be some of the flows may be at their upper bounds, but we will call these the basic arcs. So the spanning tree is the spanning tree consisting of basic arcs. Then U or okay, L is the set of arcs at their lower bound, which is 0 in our case right now, right. Yeah, so you can see, you can guess that there can be situations where the lower bounds are not necessarily zeros. We will just mention them at the end of the when this thing is over. Then U is the set of non-basic arcs. Non-basic arcs. Similarly, U is the set of non-basic arcs at their upper bounds. Okay. So we have this structure given to us, starting thing, and we also need to discuss later on how to get a starting spanning tree structure like this. We will do that. So anyway, then given this, they compute the dual solution. So I was mentioning it last time also. Compute the dual solution. So this we do by select to or put W1 as 0. Okay, so we will always do that, and so we call this we also call this the root node, and therefore the spanning tree is also called a rooted tree. And the significance of this comes in later on, but anyway, right now we are saying that W1 is 0, right. So then you can compute the remaining remaining n minus 1 Wi's uniquely, right. So you can do that because you will have for the basic tree you have n minus 1 arcs, and once you fix one of the Wi's, you have n minus 1 W variables to decide given n minus 1 equations, and so because the relative prices for the basic arcs must be zeros, so we get the remaining this thing, right. And the process is not difficult because you see it's a spanning tree, so it's a connected tree, right, with n minus 1 arcs. So once you have your arc 1, and here you have put the dual variable as 0, then there will be at least one arc incident on it. Correspondingly, for this, let us say it is J1, then you will fix, you will say that W1 minus WJ1 is equal to C1 J1. So that tells you that WJ1 is minus C1 J1. Similarly, because it is a connected thing, there will be an arc like this or like this. So you just go on because the tree structure is given to you. So you can, and again as we mentioned that the basis is triangular, so backward substitution you are essentially doing, and the backward substitution you are starting from node 1 onwards. So you can accordingly fix as you go along the tree, you can fix all the dual variables also. So we do that, and then yes, so after that compute Cij bars, right, and we said that if Cij bar is greater than 0 for Xij 0, right, for a non-basic variable which is at its lower bound, then you cannot, because increasing a value here would also increase the objective function value. So this is optimality criteria for Xij 0, and if Cij bar is less than 0 for a basic non-basic variable at its upper bound, then also we cannot improve the value of the objective function, because if you want to reduce this value, then Cij bar negative, the product will become again positive, and it will be a positive increase in the value of the objective function, right. If this, then the current solution is optimal. Okay. So therefore, we will look for, we will always at the end of, once we have obtained a basic feasible solution, we will check for optimality. If we find some arcs violating the optimality condition, then we will consider them for entering into the basis. So now here, as I said, right now I will follow Danzig's pivot rule, which says that to select the arc, select the arc which violates optimality criterion the most. That means it may either be a Cij bar negative, which is the most negative, or it may be a Cij bar positive, which will be most positive. So that means you will have to compute all the Cij bars for the non-basic arcs, and then select the one which violates the optimality condition the most. Okay. So Danzig's rule, and as I told you that the other pivot rule could be that you, the moment you find one arc which is violating the optimality condition, you enter it. And of course, there can be in bit. So these are the two extremes. You first compute all Cij bars and then find the best one to induct, best one in Danzig sense, or you just the moment you find one arc which is violating the optimality condition, you try to enter it. So there are also in between rules, and one can, I will give you some more references later on, so you can go through them. Okay. So that's it. So once therefore we use Danzig's pivot rule. So we decide on an arc to enter the basis. And now what happens when an arc enters the basis? So that means you will add. So suppose, consider, now let us say that Cij bar is less than 0, and currently Xij is 0. So it means this is a non-basic variable at its lower bound, and the corresponding Cij bar is less than 0. So increasing the value of Xij will improve the objective function value. So in that case, if you consider T union Ij, right, has a cycle. See, I went through all this in detail for the transportation problem, where I demonstrated to you how a theta loop would be available, and the same kind of thing happens here. So we will not spend time on rigorously establishing that this will have a cycle, but anyway, because this will be now n cells and so n arcs, and so they must be linearly dependent, because the rank of the matrix is n minus 1. So this will have a, and cycle we showed you is a minimal, in this concept of minimal dependent set. So that means it will be the set of columns which have two entries, two entries. Each column of this set consisting of the cycle will have two entries, 1 plus 1 minus 1. And so when you add up, you can add up all the rows, it will be 0. Anyway, so this has a cycle, right? So now let's consider a configuration. Suppose this is I and this is J, right? And then you may have J1, and then you may have J2, and this may be J3, and then this. Okay. So this is your cycle. And now what we talk about, I have already mentioned all these things, so I am just going through them so that you have a, you can recall all these things. So the thing is that we want to increase the flow along this direction, right, on the arc Ij, because the Cij bar is less than 0. So then we give an orientation to the cycle, which is the same as the orientation of the arc, because we want to increase the flow in this direction. So that means, and now the idea is to determine by what level you can raise up this value. So suppose I want to increase the flow by delta here, then this arc also has the same orientation as the cycle or as the arc ij. So therefore also here also the flow will increase. But now this arc has an orientation which is opposite to the orientation of the cycle, therefore this will, the flow here will decrease, and so we indicate that by minus delta, because see the arc is in this direction. So if I try to flow something, which means I am actually reducing the flow on this arc, right? Then here this also has the same orientation, so this will be plus delta and this will be delta. So all these arcs will have. So now what are the considerations? As usual, again the same, see it's the same simplex algorithm. I first showed it to you how it can be implemented on a transportation array. You saw the simplifications, tremendous simplification. Now I am just trying to show you how to implement the simplex algorithm on a graph, on a network. This is the difference. Otherwise the theory and everything remains the same, right? So in any case, you want to just quickly recall. So here you see you will have three values. Delta 1 will be the smallest value for which a basic variable, a basic arc. So that means I am considering, see here you have this kind of thing, and you may already have a flow here j1. So then you do not want, and here this would be the flow now will go up to plus delta, right. So then we do not want the flow on this arc to go beyond its upper bound. So we are saying smallest value for which a basic arc reaches its upper bound value. So that means you are going to say that this is uj j1. So which implies that delta is less than or equal to uj j1 minus, or let me write it properly here, okay, which implies, this implies that delta is uj j1 minus xj j1, right. Delta is this, so less than or equal to. So then among all such deltas, that means among all the positive deltas, so here for example this will be, your delta would be less than or equal to uj3i minus x, whatever the flow here, xj3i, and so on. So for all positive deltas you will compute the smallest one, because none of these constraints should get violated. So delta 1 is the smallest value for which a basic arc, delta 1 is the smallest value of delta for which a basic arc reaches its upper bound, right. Similarly, delta 2 would be, now here you see that for the ones for which it's negative, see here the new value is xj2 j1 minus delta, right. I am trying to flow delta units along this, which means that you are actually reducing the flow on this arc by delta. So this is this. Now this should remain greater than 0, which implies that delta has to be less than or equal to xj2 j1. So whatever the flow on the arc j2 j1, your delta cannot exceed that for all the minus ones, right. So delta 2 is the smallest value for which no basic variable, no basic arc has negative flow, right. So you want to make sure that when you increase the flow on a basic, non-basic arc, none of the basic arcs has a flow less than 0, right. And what is your delta 3? I am increasing the flow here. So delta 3 is actually your, here it will be uij, or in other words delta 3 is the upper bound constraint for the incoming arc. You are increasing the flow here. So in I can say that this is going to enter the basis, it's going to become basic, depends on how or the choices, right. And now let's quickly write down. So how, and similarly you can write down these values when, so I have considered the case, or okay, maybe I'll draw it again for you here and we'll quickly revise the considerations. So now you can also have a situation when the arc has a flow like this, and maybe let's consider the same situation. J2 has, okay, this one, and now this is the case when Cij bar is greater than 0, and the flow Xij is Uij. So that means this is saturated arc. And if the Cij bar is greater than 0, reducing this value will give a decrease in the value of the objective function, right. So therefore now your orientation will be reversed, right. I'll do it this way, fine. And so this will be minus delta, right. Here again this will be minus delta, and this is also opposite, yeah, but this will become plus now, and this will be minus delta. So I want to decrease the flow on our on arc Ij, then I will use this device, so that I say that the orientation now becomes opposite to the direction of Ij, because I want to give flow into the cycle in this direction. And yes, and you can yourself observe, just like theta loop, that because I am changing the flow along a cycle, at every node conservation is there, and so your constraints will not be violated, the constraints will remain intact. So here also what we are doing is we are saying that this has to be like this, and which means that the flow here will go down by delta, and so again when you want to determine, you will have the 3 numbers again. See here delta cannot, so here delta cannot be greater than Uij, right, because otherwise the flow here will become negative. And then for all these minus arcs, see here the flow, so therefore here the delta will be governed by the amount of flow that you have in this direction, because the same consideration as you had for the arc J2 J1. See here we said that delta has to be less than or equal to Xj to X. So wherever there is a minus sign, the delta will be governed by the amount of flow that is there already in the arc, right. So in our case, this one, the flow is here Uij, and on this it is Xj3I, and so on. So for minus ones, the value of the delta has to be governed by the amount of flow that is already there in the network. For plus 1 here, your consideration will be that this arc should not again exceed its upper bound. So here you will have the that delta must be less than or equal to Uj2 J1. In other words, your whatever the flow J2 J1, this is the flow, plus delta should be less than or equal to Uj1 J2, and so on. So once you understand, because the theta loop part was very well done with you, so you understand that this is the thing. So once that means depending on what kind of arc we are entering into the basis, we will compute these things and decide. And so now once you have decided the value of delta, so then you update, that means update the flow in the network, right. So this is the next step, update the flow in the network. Now you have to recompute the dual solution. So just as in the case of the transportation problem, I showed you a shortcut. So here also there is a shortcut. We don't need to compute the dual solution from scratch. We can take advantage of our earlier calculation. So for example, what we are saying is that if suppose you have something like this, suppose this is a tree solution, right, and suppose this arc is a candidate for entering the basis, right. So then yeah, and I should have told you that wherever the say for example out of these three, yes, I should have mentioned this also. So say for example, if delta is equal to delta 1, that means the minimum of the three. So yeah, I should have written that down. So final choice of delta is minimum of delta 1, delta 2. I hope you can read it. This is delta 3. So out of these, once you compute these three numbers, then choose the smallest one of the three, and that will be the value of delta, right, at which this variable will enter the, or this arc will become a basic arc, and the flow will get determined. So here for example, if delta is delta 1, then what is happening? If delta is delta 1, that means one of the arcs is reaching its upper bound before any of these two things is happening. So what will we do once this happens? So again, I will not write it down because it's the same steps for the, as we did for the transportation. So once an arc reaches its upper bound, we will rename it as a non-basic variable and drop it from the basis. So that means suppose it is this arc which is reaching its upper, for which this minimum is attained. So then this will reach its upper bound when I update the flow. So this will become non-basic, this will become a basic arc, and this will become non-basic, right. So again, I'll have to recompute my, so that means this is my incoming variable, this is my exiting arc from the basis. If the minima occurs for delta 2 out of these three, if delta 2 is the smallest number, that means some arc is going to become 0 when I have the flow at level delta in the cycle. So that means one arc will become, and so you can say that for example here, smallest value for which the basic arc has negative flow will become negative. So that means before that happens, so here that means this arc therefore becomes non-basic and this arc becomes basic, the usual pivot, right, because this will become 0 and this has become positive. And if delta is minimum for delta 3, then this has reached its upper bound before anything else happens. So that means I don't have to change the status of ij, the arc ij remains non-basic, but now it reaches its upper bound. So there's a positive flow on the arc which is equal to its upper bound, but I don't change the status of the arc, it remains non-basic. So these are the three things that will, so this describes your pivot rule completely, and accordingly you can also manage the pivot rule here, right. So now you have recomputed. So how do you recompute the dual solution? So idea is that I'll give you the simple rule here, try to write it in this much space. Okay, so this is, suppose arc ij is entering the basis and arc PQ is leaving the basis. And you have seen that it can be in two different ways. Either the arc is becoming, the flow is becoming 0, or it is reaching its upper bound. Two things can happen. Okay, so it's leaving the basis. Now what you do is, in the current, I mean the tree, before you do this actually, arc ij is entering and this arc PQ is, so drop PQ from the current tree, which I mean is that before you have done the pivot, before the pivoting, drop PQ from the tree before the pivoting, before the pivot, right. So you are dropping this in that, and then this will decompose the tree into two trees, T1 and T2, right, where node 1 belongs to T1. So your root node, okay, node 1 belongs, so we will call that subtree T1 for which, in which T1 lies, right. So and the other one is T2. So that will always happen, you see, because it's a minimal minimally connected tree subgraph. So, like for example, if I drop this arc from the tree, then I'll have this portion and I'll have this portion, right. Look at, I drop this arc, then I'll have T2 will be just simply this node and T1 will be this, because 1 belongs to T1. So, you'll always have 2 subtrees the moment you drop the exiting arc from the basis, right. So, then and now you have 2 cases, Q belongs to T2. See, so therefore, okay, before I say that, yeah. So, Wi's for I belonging to T1 do not change. Why? Because this remains 0. So, since T1, all these arcs are connected to node 1. So, therefore, your dual solution, their dual equations remain intact, and so these dual variables will not change. So, Wi's for I belonging to T1 do not change, because my value here of the root node, the dual variable corresponding to the root node does not change, right. Now, if Q belongs to T2, so there are 2 possibilities. If the arc is like this, say for example, and let me say that this is the exiting arc. So, let us say 3, 5 is the exiting arc and this is coming in, okay, in this one. So, what we are saying is that here either, so what is it, if this is leaving the, if we are dropping this, then what is your T1? See, I have dropped this, so your T1 is this, these 3 arcs, and your T2 will be simply this one, right. T2 consists of the arc 5, 6, and so now you, if the arc is in this direction, then your node 6 belongs to T2, and if the arc will be in this direction, then what we will say is that, see, if I call it PQ, then P will be in T2. So, that depends on the notation. So, if Q belongs to T2, then what is happening? So, then you see, because P is not in T2, so the value of P, the WP has not changed. Then you have the equation WP minus WQ, right, less than or equal to, okay, yeah, you have it less than, yeah, that was the equation, but anyway. So, then let me write it this way, then CPQ minus WP plus WQ is CPQ bar, and which is less than 0, because that is why we decided that PQ will enter the basis, it was at 0 level, fine. So, then this is this, and if WQ prime is the new value of WQ, then what is the equation that needs to be satisfied? Then we want that WP minus WQ prime should be equal to CPQ now, because PQ is going to become a basic arc, right. This is it. So, which implies that your WQ prime is equal to WP minus CPQ, and from here WP, if you take it to this side, is equal to WQ minus CPQ bar. So, that means the new value of WQ prime is WQ minus CPQ bar. So, the value of WQ changes by you subtract CPQ bar from it, and so this is the new value that you have, right. And we have already discussed this again in the transportation problem, that now in this T2, if for example this value has changed, then this value will also change, because they are connected by the same amount. So, that means what is our rule now? For all nodes in T2, the dual solution. So, when we are recomputing the dual solution, so what comes out is that Wi's for I belonging to T1 do not change. So, you do not have to spend time computing them, and for and Wi goes to Wi minus CPQ bar for I belonging to T2, where we know that PQ is the exiting variable. Oh, sorry, what did I say here? Yes, let us be clear, is ij is entering. So I should have, and the base, so we drop PQ, and I should have, yes, I should have said, if I say that it is ij which is entering, then if j belongs to T2, then I have to recompute. So maybe it will be easier to, I'll keep it as QT2, I'll leave this. So here we will say that ij is the, okay, is the exiting, is leaving the basis, and our PQ is entering. Okay, so make it the other way. So then drop ij from the base, from the tree before the pivot. This will decompose the tree into two trees, and we will call T1 that tree in which one lies, and the other tree would be, other subtree would be T2, and then we are discussing like this. So if Q is T2, so yeah, so therefore we have to, yeah, so then these values will change by C bar PQ. So we said that you see, when the arc PQ is entering the basis and ij is leaving the basis, then by dropping arc ij from the tree, you see it will get disconnected into two parts, we said, and then so T1 and T2 will be the two parts of the tree, and node, we call T1 that subset of the tree in which the node 1, the root node lies. So therefore T1 will be that particular tree, and T2 is the other one. Now the Wi's, so to recompute the dual solution, I am giving you a simple formula. So this is Wi's in T1 will not change, it is only the Wi's for the for the nodes in T2 which will change, right. And so here I am saying that see, for I in T2, the calculation I have already shown you, the Wi will change, will reduce by CPQ bar. So that means the new Wi would be Wi minus CPQ bar, right. And then of course we will continue with the algorithm, but in case P belongs to T2, that means the arc PQ that is coming into the basis. So either the node P belongs to T2 or the node Q. So in case node Q belongs to T2, then we update the corresponding dual value by Wi minus CPQ bar, right. And in case P belongs to T2, then W prime P minus WQ, you see, well, the calculation is simple. The new WP prime, the value of this WP prime minus WQ is CPQ, right, because the arc is coming into the basis. So the new dual values should satisfy this particular dual constraint as equality, right. So therefore it follows that W prime is WQ plus CPQ. Now when you substitute for CPQ bar, then the WQ will cancel and you will have WP plus CPQ bar. So that means WP has gone up by C bar PQ, right. So if P belongs to T2, then the dual variable will, the value will go up by C bar PQ, and since your T2 is connected, that means that all nodes in T2, the dual variables will go up by CPQ bar. So this is how, if you can remember this simple formula, then you do not have to recompute the dual variables for all the nodes, you only have to recompute them for the nodes in T2, and that also the formula is simple, that if P belongs to T2, then the values go up by C bar PQ, and if Q belongs to T2, then they reduce by C bar PQ for I belonging to T2, right. So so therefore a real shortcut to recomputing your dual solutions. Here again we are taking advantage of the structure of the problem, right. So we are exploiting the structure and simplifying our computations. Okay. So now this happens, so then we continue. So then continue with the and I have already said that you update your flow in the network, recompute the dual solutions, and then continue with the algorithm. Okay. Now there are few issues that we need to look at, and so I will first work out an example for you quickly. So I will show you one or two iterations of the algorithm, and then we need to look at how to compute the starting dual feasible solution, right. That means I must get a starting structure TLU and given a problem to solve, and secondly we have to tackle degeneracy. Okay. And again it's nothing different, it's just that here again people take advantage of the structure and try to come up with a simpler rule for combating cycling. So okay, they take up this example. Now here the numbers are Cij, Uij. So the first number is the cost, the second number indicates the upper bound on the flow that can take place on that arc, right? And these numbers are the BIs. So here for node 1 it is 25 units, that's the only source. The other, these three do not have anything available. Then 5 and 6 are in our sense markets or the demand points. So then they add up. So sigma BI is 0, right? And you are told that this is the initial solution. So T is this, and U contains these three arcs which the flows are at their upper bounds, right? And this is the arc which has 0 flow, 3, 4, right? So I have tried to draw the thing here, and let us see. So 1, 2, and what we will do is we will indicate the, okay, I find it convenient to represent this as a broken line, right? And so the 1, 2, for example, so you had 20 units, this is upper bound. So that means the flow here is 15. So then this flow is 10, right? And so the round circles indicate your basic arcs, and the square ones indicate the non-basic arcs at their upper bounds. The flow is at their upper bound, right? Then you have 3, 2, the flow is, and then you have 2, 4, 2, 4, the flow is at its upper bound, which is again 15. So I can fill up this, and then you have 4, 6, the flow is 10, which is, so we'll again denote this by broken line, and this is also a broken line, right? Okay. So then you have 10, so 10 go up this way, right, because this is the only thing. So 10 going this way, then 2, 5, you have how much? Now this is 15, this is going 15, so this must have 10 units of flow, right? Remember conservation. So if 25 units are coming in here, then 25 units have to go out. So this is just becoming familiar with the when you're trying to do the algorithm on a network, right? Now here 5 units were required, and so you have 2, 5, then you have 4, 5, and 5, 6. So 4, 5, you have 10 units coming here, then you need 10 more here, so this will be 10, right? And so 10 going out, so you must have 5 units coming here, right? Because 5 units are demanded here. So 10 are coming, so this way you have 5 more units. So 15 are coming, then 5 get absorbed here, and 10 go on this way. So this is your starting feasible solution, right? And 3, 4 is 0, and in fact 3, 4 and 3, 5 both. We have not yeah, I should have included 3, 5 also. Both these arcs are at their lower bounds, which is 0 right now. And we to compute the dual solution, we'll quickly do this, right? And then you see that here, I'll just write it out. So the cost is 3. So that means 3 minus 0 plus W3 is 0, the basic arc, right? Which says that W3 is minus 3. So it's minus. So for these arcs it is, so I'll write it, this is minus 3. The same thing, we were doing that on a transportation array, now we have to do it on the network, right? So here again, this cost is how much? 3, 2 is 6. So you want that the Cij value, that means the Cij value 6 is equal to essentially Ui minus 3 plus W2. So W2 becomes 9. Is it okay? Yeah. W2 becomes 9, but then it should not be 9, it should be minus 9, I think, according to me. This is 6, so yeah, okay. We want the relative price to be, so 6 plus 3 plus W, oh sorry, this is minus, okay. So therefore, yes, so your W2 is minus 9. and I'll tell you why I could realize that this is not correct. The plus 9 was not correct. I'll get back to you in a minute. Oh, so yeah, similarly, let's quickly do this. Yeah, so this is because for the transportation problem it was all plus, we had got rid of the negative sign, but here the negative sign is intact. So therefore, yeah, so for 2, 5, what is the calculation? So 2 should be equal to minus 9 minus W5. So minus W5 is, or W5 is minus 11, right? And for this one again you'll have to write out 7 is equal to minus 11 minus W4. So that gives you W4 as, no, something is wrong, because, yeah, so W4 is minus 18. Let's see, let me write it again. See, what we are saying is C45 minus W4. That's again I was not writing it correctly. So this is because the arc is 4, 5. So minus W4 plus W5 is 0, right? So therefore, this implies that W4 is equal to C45, which is 7, and this is minus 11. So this is minus 4. W4 is minus 4. We'll check this in a minute. Okay, then yeah, I should have written out the values. Fine. So then this for 5, 6, what is happening? The cost is 1. So 1 should be equal to minus 11 minus W6. So therefore, W6 is equal to minus 12. Minus 12. So given this basic feasible solution, I compute the relative prices, and you see that from here for 3, 4, yes, that is positive. So that will not be a candidate. C35 bar is minus 3. So this can be a candidate for entering the basis, and C bar 2, 4 is 9, and since this is at its upper bound, the positive number here implies that when I reduce the flow, the cost will also come down. So these are the and 4, 6 is at its upper bound, and minus 5 does not help. So therefore, the arcs that are candidates for coming into the basis, that means arcs 3, 5 and 2, 4 are candidates for entering the basis, and so we will choose arc 2, 4. That means I will reduce the flow. But before I continue with the algorithm, I just want to make a note here that there is a nice interpretation for the dual variables for the network flow problem. So here you see minus Wi will be the distance of node I from node 1. That means suppose I take the numbers which are the costs, I can treat them as distances. So whether I call this as the distance of node I from node 1 or the cost of reaching node I from node 1, whichever way you want to interpret the numbers here, theCij's, then you see for any basic feasible solution with respect to the given tree, minus Wi should measure up to the distance of node I from node 1 with respect to the tree, right. So for example, in the in this solution here, you see 1, 3. So here this is, and we start with W1 as 0. So then this is minus of this is 3, which is the distance of node 3 from node 1, right. Then you can go up. So to reach node 2 from node 1, this is the path you will take. So you add up the cost, which is 3 plus 6, 9. So minus 9 is your W2, right. Then similarly, when you come to node 5, this is the path. So here this would be 3 plus 6, 9 plus 2, 11. So minus 11 is your W5. Now when you go to node 4, you see this arc you traverse in the opposite direction. So that means here I will, when I want to compute W4, the distance, or okay, W4 is minus 4. So yeah, so maybe I should write here minus 4. Now this is, or okay, whichever way you want to do it, fine. Yeah, this will be minus 3, or okay, minus 11. I have already come up to here, minus 11. Then this is traversed in the opposite direction. So I will have to write plus 7 here. Okay. and so this will be minus 4. Or you want to do it this way, that 3 plus 5. So, this is 11, right. So, if 11 and then minus 7, so that is 4, so minus 4. So, the distance or the cost of reaching node 4 from node 1 is 4 in our term, right. And similarly, this is 12, that means the currently. So, every time when you recompute your dual solution, this will be a very good check, because you have small networks, you can do it by hand. So, therefore, you will know immediately that given the tree solution, with respect to the tree, you find out the path for each node from node 1 and then add up the cost of the arcs that make up that path, and it should measure up to. So, minus of that sum should measure up to the dual value, the current dual value, right. Okay. So, this was just I wanted to show you that the dual solution has a very meaningful interpretation here. Okay. So, now we continue with the algorithm. So, I decide to choose 2 4, because right now I am using the Danzig's rule, which says that you bring the most profitable arc, inverted commas, right. You will bring in the most profitable arc into the basis. So, since C bar 2 4 is 9, so here the rate of reduction in the cost would be at 9 units, this thing, and C bar 3 4 is only how much is it? That is 2, right. No, you sorry, C bar 3 5, C bar 3 5 is 3 minus 3. So, therefore, we will choose C bar 2 4 has to be reduced, and so the cycle formed here would be this when I consider this, and the orientation has to be this, because I am reducing the flow on 2 4, right. So, then on arc 2 4 the flow will go up, and on arc 4 5 again the flow will go down, right. And delta here comes out to be 5, because remember we have to make sure that the flow here should not become negative, the flow here should not exceed its upper bound, and similarly here also the flow should not become 0 negative, right. So, the numbers are 5 5 10, and you take the minimum of the 3 numbers, then 2 5. So, when your delta is 5, 2 5 will reach its upper bound, because currently the flow is 10, and if I add 5 more units, 15, the upper bound will be reached, right. So, now I have 3 choices here, and 2 4 becomes basic, because flow here has now come down from its upper bound, and 4 5, what is happening for 4 5, what is the current flow? The current flow is 5. So, if I reduce the flow, then this becomes 0. So, you see you have either you have a choice of allowing making 2 5 a non-basic variable, or dropping 4 5, which is a non-basic variable at 0 level. So, we decide to, and this is where you see the problem in the simplex algorithm can come, because your choice of exiting variable is not unique. So, here drop arc 4 5, and similarly for the incoming variable also. So, we decide to drop arc 4 5, is it okay? And I have shown you the updated solution here now. This is 15, I am keeping it as basic, 4 5 has been dropped, this arc the flow has come down by 5 units. So, this is it, right. Now, remember the shortcut that we have used. So, what is happening is that when you see the drop in the arc which is being dropped is 4 5. So, when you drop this from this tree, see we are dropping arc 4 5 from here, then in the current tree this remains intact, it is only node 4. So, node 4 now becomes your T 2, and this is your T 1, because 1 belongs to this part of the tree, right. So, T 2 simply contains node 4, and since your the incoming arc is 2 4, remember it was non-basic, now we are making it basic. So, the incoming arc is 2 4. So, that means Q belongs to T 2, and so that means that the corresponding value for W 4 prime will go down by C 2 4 bar, and this is C 2 4 bar is 9. So, minus 4 minus 9 is minus 13, and this is your updated dual solution. Nothing else changes, because the whole of the tree, all the other nodes are in T 1. So, their WIs remain intact, and this is the only one which changes. And now you can again just do that exercise, that the distance from here to here should measure up to 13. Right, and other distances remain the same, because that is the only change you have made, right. Okay, 4 5 has been dropped, fine. So, now that means I recompute my dual relative prices, and here you see that 3 4, yeah, 3 4 is a non-basic variable, the value is minus 7, C bar 3 4. So, therefore, this is a candidate for coming into the basis, and again we are using the most negative here, I mean absolute value, largest value. So, this is minus 7. So, therefore, arc 3 4 enters the basis, right. And now, when you compute the delta, so I will let you do the computations yourself, but I am giving you the numbers. So, delta is minimum. So, all the 3 numbers are the same, and here again you have, you see, a lot of choices. Your choice of deciding on the exiting variable is not unique. We let arc 3 4 remain, and of course, because see here what is happening is that 3 4 is also when you allow 3 4 to enter at level 10, then 3 4 reaches its upper bound, and all others also either flow becomes 0 or attains its upper bound, whatever. You can check out what are the choices here. So, in any case, see, we will have to do least work when we decide not to make not to change the status of 3 4. It is just that the flow on 3 4 becomes equal to 10, that means it is equal to its upper bound, right. And so, we will not have to change anything, we will not have to change our dual solution, because no arc is leaving the basis remains intact, right. So, but then what will happen is, remember, if you allow 3 4 to enter, maybe I can just show you here. See, this you are allowing to enter. So, your orientation will be this way, right. So, this becomes this and this comes down like this, right. And so, what is happening that both of them are at 10. So, since you are increasing the flow on this arc by 10 units, this flow becomes 0 and this flow becomes 0, right. So, you will have to then decide on one of the variables, because you have to maintain 5 arcs in the basis. So, that you have connectivity. So, therefore, I will increase the flow by 10 here. So, 3 4 and okay. So, this will remain non-basic at its upper bound, but here the flow will become, I will not disturb this one, next next diagram I will make, but I will keep 2 4 and 3 2 at 0 level, but in the basis. So, this is what we are doing, we are not changing. So, therefore, we do not have to do any calculations, it is just that this number now, the flow on arc 3 4 is also equal to 10, and both these flows come down to 10. So, now I have updated the solution here. Remember, these two became basic, but at 0 level, right. So, this is the solution. Now, because my dual solution did not change. So, I have from earlier calculation, your C bar 4 6 is equal to 4, 4 6 is at its upper bound. So, this would help in reducing the cost, and now you see, when you want to reduce the cost, your orientation of the cycle would be this, right. So, this would be minus delta, this would be plus delta and plus delta, but you see that here delta would be 0, because this is already at its upper bound. Here there is no flow on arc 2 4. So, I cannot reduce by the flow by any amount. So, therefore, delta by here is also 0. So, therefore, this is a degen. So, that means delta is actually minimum of 0 0 0. I hope this point is clear, right, because the orientation has to be this. I am wanting to reduce the flow on 4 6. So, here also it will be minus delta, there is no flow on 2 4. Then when you want to come down this way, the delta has to be positive. So, plus delta, but the flow is already at its upper bound. So, therefore, the value of delta is 0 0 0, I mean the minimum value, which is equal to 0. Right. So, therefore, this is a degenerate pivot, but it will help us to change the status of certain arcs. So, that we get a new basic feasible solution, new in the sense we get a new tree. So, let arc 2 5 exit, we are saying that because at its upper bound. So, I can make it non-basic, and arc 4 6 enter the basis. So, we are not changing the flow at all, it is just that now I am calling this arc as basic and this arc as is non-basic, and this arc 4 6 as basic, because trying out a new basis. And so, I wanted to show you this step also. So, now here when arc 4 6 enters and you are dropping arc 2 5. So, just see from here arc 2 5 is being dropped, then you see your tree T 1 remains 1 3 2 4, and only 5 6 are the this is the arc which make your T 2. I mean the T 2 is your 5 and then arc 5 6 and node 6. So, these are the, and what is your entering arc 4 6. So, again Q belongs to T 2, okay. And therefore, as I am saying here, that incoming arc is 4 6 and 6 belongs to T2. So, therefore, W5 and W6 will decrease by C bar 4 6, which is 4. So, I have done that. Earlier value was minus 11, it has become minus 15 and this was minus 12. So, this is minus 16 now, right. Okay. So, I think I have shown you enough iterations how to update your dual solution, how to update the flow and so on, and also try to demonstrate to you the shortcut in computing your dual values. Then I would like you to make maybe 1 or 2 more iterations. I think 2 more iterations from here to reach the optimal solution, and I have given an optimal solution here, but of course, it need not be unique, because remember the choice of exiting and entering variables has not been unique in all the iterations, but you can try out and see. So, anyway, this is one of the optimal solutions and you should try to complete the this thing. So, basically I have tried to just translate the simplex algorithm to the network flow problem, min-cost flow problem, and try to show you that because of the simple structure you can take advantage of the calculations, just as we exploited the structure of the transportation problem, because there the underlying graph or the network was simply bipartite. Here of course, it is not bipartite, but still we could exploit the structure and make shortcuts in your computation. So, I think the algorithm should be quite clear how we go about it. So, as I said, there are 2 considerations: degeneracy has to be tackled, and also a starting feasible solution, and we will use here phase 1 just as I showed you for the transportation problem. We can use phase 1 and that is not difficult, but later on I will give you, as I said, for the bounded variable transportation problem also, I will give you this max flow method of computing the starting feasible solution, which will hold for this one also, because the only difference between a bounded variable transportation problem and a min-cost flow problem is that for the transportation problem it is a bipartite graph. So, just the computations become a little different, otherwise it is almost the same thing. So, the idea of including this in the course was, I could have simply said that you just apply the algorithm as for the bounded or as for the transportation problem to this one also, but I wanted to show you how you can work on networks directly and see the implementation of the algorithm.